In this video, we'll see a concept that follows from the ideas of Theorem 6.11. The idea here is of a t-tough graph. So recall Theorem 6.11, that was if G was Hamiltonian, then the number of components in G minus S is at most the cardinality of S for any non-empty proper subset of vertices. We can write this a little bit differently and sort of bring this number of components over to the other side and see that this means that the ratio of the number of vertices in S over the number of components in G minus S would be greater than or equal to 1 if G is Hamiltonian. That is, we would have this is always greater than or equal to 1. And so the idea for all non-empty proper subsets S. And so the idea is we give a parameter to this over all subsets S. We name this parameter. And so here we give the definition. A non-negative, for non-negative real number t, a non-complete graph G is called t-tough if this ratio mentioned above is at least t for every vertex cut S of G. So here, notice we're restricting ourselves to vertex cuts. That seems like reasonable to do because the number of components would be 1 for every non-vertex cut. And so this is an okay restriction. And this is the idea. And so what follows, we can restate Theorem 6.11 in terms of this t-toughness. So Theorem 6.11 now becomes if G is Hamiltonian, then G is 1 tough. But of course the converse of this is not true. As I mentioned in the previous video, the Petersen graph is 1 tough, but the Petersen graph is not Hamiltonian. So we're going to prove that in a second, and then you might be wondering what's the purpose of this new parameter, this new definition. And the idea is that there is a outstanding conjecture for a sufficient condition for a graph to be Hamiltonian that involves this parameter. So let's jump to the Petersen graph. Let's see that why the Petersen graph is 1 tough. All right, so some preliminary stuff to take care of first for showing this is 1 tough. So remember what this means is I want to show that given any cut set, any vertex cut of the graph, if I take the ratio over the number of components in G minus S, I want to show that this is greater than or equal to 1 for all vertex cuts S. I want to show that this is true. All right. Well, remember that the connectivity of the Petersen graph, so a couple points here, connectivity of the Petersen graph is 3. So that means that, right, remember that means the smallest number of vertices whose removal disconnects the graph is 3. That is, the minimum cardinality of a vertex cut is 3. And so we have immediately that we only need to consider cases where the cardinality of S is at least 3. And then let's see it as an upper bound for S. So suppose the cardinality of S is greater than or equal to 5. So if the cardinality of S is greater than or equal to 5, well, since the order of the Petersen graph is 10, that would mean that we would have just at most 5 vertices left over. So that is the cardinality of the vertex set of the Petersen graph minus S would be at most 5. And certainly the number of vertices left over is an upper bound on the number of components, right? There's at least 1 vertex in each component. Likely less, but that's sort of worst case scenarios. Each one of those vertices gives a component. And so this implies that the number of components in the Petersen graph minus S is at most 5. So, right, so if cardinality of S is at most 5, or is at least 5, then the number of components is at most 5, and it follows then that S over the number of components, well, that'll have to be at least 1. Let me think, is there a better way to explain that? Let's see. Right, that's really just playing around with the inequality, and maybe you can just see it without too much effort, but of course, I'll just show something extra here. So, right, so I'm dividing by the number of components, that's at least 5, so this is at most S over 5, but S is at least 5, so this is at least 5 over 5, that's 1. That's how we get that answer of 1. So, okay, so what this is saying is that cardinality of S has to be at least 3, but if it's at least 5, then automatically, without too much work, we can see that that this ratio is 1. And so the only possible issues would be when the cardinality of S is either 3 or 4. So S, so I'll say we may assume cardinality of S is 3 or cardinality of S is 4. And actually, we're not going to break it up into cases based on this because there's an easier case argument that comes from examining the cycles. So I have labeled the Petersen graph in a specific way here. I have this outside cycle C. So C, and that's the U1, U2, U5, U1. That's my outside cycle, and then my inside cycle C prime. I'm going to call this V1, V2. Or sorry, it wouldn't be V1, V2, would it? It'd be V1, V3, V5, V2, V4, back to V1. So each is a 5 cycle. Now, we haven't discussed automorphisms of graphs yet. However, there's an argument to be made here that takes that into consideration. That is, there is an isomorphism from the Petersen graph to the Petersen graph such that the inner 5 cycle becomes the outer 5 cycle. So essentially, I can swap the inner, right? There's some edge-preserving bijection from the vertex set of P to itself that preserves the inside cycle, preserves the outside cycle, and swaps them between each other. So the inside becomes the outside, and the outside becomes the inside. And so it follows that that one of the outside or inside, the only 2 cases here, if my cardinality of S is 3 or 4, that we could say without loss of generality, there's at least as many vertices removed from C prime as there are C. That the 2 are essentially the same, so we'll look at the majority case being vertices removed from C. So without loss of generality, assume there are at least as many vertices without loss of generality, there are at least as many vertices removed from C prime as C. Okay. So this gives us now 3 cases. So case 1, no vertex of C prime is removed. Well, in this case, if we don't remove any vertex of C prime, that means we're removing 3 vertices of C, 3 or 4 vertices of C, but that's irrelevant because no matter how many vertices I remove of C, I will still be left with just 1 component of the graph because of this inner 5 cycle. If I don't remove anything there, I still have the 5 cycle, and then together with the spokes, I'll still have just 1 component. That is, no vertex of C prime is removed, means that then P minus S is connected. And so that we don't have to consider that case, right? The number of components would be 1. And so this ratio would be either 3 or 4 in that case, which is certainly at least 1. So case 2, let's say one vertex of C prime is removed. One vertex of C prime is removed. Okay, well, let's examine that. So one vertex of C prime is removed, and then either 2 or 3 vertices of C, the outside cycle, is removed. So if I remove just one vertex of C prime, it could be any of these, let's say that one, without loss of generality, then I still have the rest of the inner 5 cycle is connected, right? If I remove one vertex from a cycle, I haven't disconnected it. So the rest of these vertices inside here are still connected to one another. And so that's at least 1, 2, 3, 4 vertices in a single component by themselves, in a single component. And then I'm removing at most 3 vertices from the outside cycle. So look at these leftover 4 vertices. And if I'm only removing 3 vertices from the outside cycle, one of the vertices that isn't removed is adjacent to that component from the inside, these remaining 4 vertices. So that means there's at least one component with at least 5 vertices in it, if I remove just one vertex from the inner 5 cycle. Then there is some component of P minus S with at least 5 vertices. Okay, so let's see. So what does that tell me? Well, we took a graph of order 10. Remember, Petersen graph has order 10. And if, let's say, we removed three vertices. If we remove 3 vertices, that means we would have 8 vertices left. One of the components has ordered at least 5. So that would mean there would be at most sorry, let me think about that. At least 5 vertices. Oh, right. No, sorry. So, okay, so we start off with 10. I think I need to write some stuff down. So this is the order of P. And we remove at least 3 vertices. So minus 3, that gives us 7. And that would be order of P minus S. And then we would have a component with at most 5 vertices in it. And then at most we would have 2 other components. So maybe it goes 1 and 1, or maybe we can't even do that, but it doesn't matter. We would have at most 3 components. If we removed 4 vertices, this would be 6, and then we would have at most 2 components. In any case, the number of components of P minus S would be at most 3, and we removed at least 3 vertices. So this ratio, number of components of P minus S, would be at least 1 in this case. All right, so case 3. Notice we can't remove 3 vertices from C prime. C prime is the one with the least number of vertices removed out of C and C prime. So what that means is that at most 2 vertices are removed from C prime, and that if 2 vertices are removed from C prime, that means 2 vertices were also removed from C to get our total of 4. So case 3, 2 vertices of C prime are removed. Then 2 vertices of C are also removed. In particular, cardinality of S would have to be 4 here. Remember, C prime is the the cycle with the minimum number of vertices removed from it. So 2 is the most it can have removed. So the number cardinality of S is 4. And let's see. The claim is that the number of components in P minus S is at most 4. So we would have 6 vertices left, right? 10 minus 4 would be 6. We'd have 6 vertices left. So it's possible. So let's see, we remove 2 vertices from C prime and 2 vertices from C. Well, notice that if we remove any 2 vertices from C prime, no matter which 2 I pick, we would necessarily be removing, maybe let's look at C for a better picture. We remove 2 vertices from C. No matter which 2 I remove, I'm always going to be left with 2 vertices that are adjacent to each other, right? No matter how I remove those 2 vertices, I'll always have at least 2 vertices left over that are adjacent to each other. So that means when I remove the 2 vertices from C, I'll have a component of order at least 2. When I remove 2 vertices from C prime, I'll have a component of order at least 2. So remember, I only had 6 vertices left over after removing the 4 vertices. 2 of the components have at least 2 vertices apiece in them. So now I'm up to 4 vertices. And let's see, and then, right, and then, right. So yeah, what I said, yeah, it does make sense. This is the argument, right? There would be, so 2 components of order at least 2 each. That's 4 vertices. Then I have 2 vertices remaining. Maybe they're each in their own component, but that's still just a total of 4 components at most that would be left over. And so it's true that the number of components in P minus S would be at most 4. Hence, this ratio would be at least 1. So in any case, this ratio is at least 1, and so P is 1 tough. So that's the idea with the Petersen graph. So remember, yeah, just because a graph is, just because this theorem is true, if G is Hamiltonian, then G is 1 tough. The Petersen graph is the counterexample to the converse of this. It's a graph that is 1 tough, but not Hamiltonian. So the question becomes, well, is there, what if I think about 2 tough graphs? So graphs that are 2 tough, this would mean that that I'd have to, if I want to separate the graph into, say, k components, I'd have to remove at least 2 k vertices. So it's a sort of, it's a fine-tunement of the idea of connectivity. It's also telling us, it's not just telling us how many vertices we'd have to remove to disconnect the graph, but it's also telling us the number of components that would be left over in removing a certain number of vertices from the graph. So that's a way to think about this toughness. And actually, there is a definition for the toughness of a graph. It's the maximum value for which G is T tough. I'm not going to get a lot into toughness because we don't really need it. But it's sort of a fine-tuning of connectivity. So the question becomes, and right, it tells us how well connected it is. And it tells us even more information about how well connected the subgraphs of the graph are. So yeah, the question, if a graph is, say, 2 tough or 3 tough, certainly if G is Hamiltonian, or yeah, I guess I can't say that, but right, is there any high enough toughness for a graph to guarantee that it is Hamiltonian? And this is the, talk about that graph in a second. This is the T-tough conjecture. There exists a constant T-naught such that every T-naught tough graph is Hamiltonian. So the Petersen graph shows us that if this is true, And we don't know if it's true, right? This is a conjecture. If you want, you can do your project on this. If true, then T naught is strictly bigger than 1. We've already shown that 1 isn't high enough. The Petersen graph breaks it. But is there a bigger constant that works? Well, a group of researchers in 2000 showed that if the conjecture is true, then T naught has to be strictly bigger than 2. So what they did is they gave an example of a graph that was too tough, but not Hamiltonian. And here's the graph taken directly from the paper. Our book shows a little bit different of a drawing of the graph. But the idea is to take this graph, which they called L, and copy it 5 times, and pick a pair of vertices, the specific pair of vertices in each copy of the graph. And we're going to join all these up. So these 10 vertices in this little, in this thing here, this forms a K10. So all of these vertices are joined up. And then we have these 2 other vertices, this K2, and these are joined to every one of these graphs. So they were able to show that this graph is too tough, but not Hamiltonian. So it does take a second to see both of those properties. If you stare at it for a while, you might be able to convince yourself, but the proof is not, it's not trivial to see that this is too tough. But you can sort of run through a lot of the cases like we did with the Petersen graph to conclude that this is too tough and it's not Hamiltonian. So this is the idea that by the way, these researchers actually did a little bit more. They found an infinite class of graphs. Each one of is this increasing or decreasing? They found an infinite class of graphs whose toughness approached 9/4. So they were also able to show that if the conjecture is true, then T naught is at least 9/4. They were also able to show this. They found a sequence of graphs that gave this that approached 9/4. Okay, so yeah, this is still an open conjecture. There have been a lot of papers put out there. I think last I heard there were about 100 or so papers put out there on this topic of toughness and trying to get a handle on this theorem to be able to prove a sufficient condition to be Hamiltonian in terms of the toughness of a graph. So I don't know, it's difficult, but it's something we still haven't solved. All right, that's it for this video.